In this video, we shall understand the concept of calculus through a story. This is Differential Calculus Simplified by Maths Simplified.
An apple falls. Centuries ago, moments like this changed how humans understood the universe. For a long time, motion was a mystery. Then came Galileo Galilei. Legend says he climbed the Leaning Tower of Pisa and dropped two objects of different weights. They hit the ground at the same time. Galileo realized that falling objects accelerate at the same rate, regardless of their mass, neglecting air resistance. If speed keeps changing, what is the speed right now? A few decades later, another mind took up the challenge: Isaac Newton. Watching apples fall,
Newton decided to perform an experiment. He climbed to the top of his house and dropped a stone, carefully measuring its time of flight. His goal was to find formulas that could predict velocity and displacement at any instant. He began with the basic relations he had learned in school. Speed equals distance divided by time, and acceleration equals velocity divided by time. Using these ideas, he derived an algebraic relation and compared it with his observations. But he soon noticed that the predicted displacement did not match reality. We call this attempt Case 1. Newton realized that these formulas were not enough. He observed that velocity increased continuously and that the stone took more time to travel the first half of the distance than the second half. From geometry, he knew that velocity is the slope of the displacement time curve, and acceleration is the slope of the velocity time curve. He knew how to compute the slope of a straight line, but not of a curve, so he applied the straight line slope formula over small time intervals. He found that velocity changed depending on where it was measured. Using this method, he calculated velocity and acceleration. This approach is called Case 2. At first, he dropped a stone from 3 different heights and measured the time of flight. The velocity is calculated at 2 points using a simple straight-line slope formula, as we discussed earlier. Similarly, he calculated acceleration. He increased the experiment to 5 heights and carefully tabulated the results. Using this, he calculated velocity and acceleration using his new formula. Next, he extended the measurements to 11 points. And finally to 1,001 points. When he examined the table again, he noticed something remarkable. As the number of samples increased, the values began to converge toward a single value. Newton realized that velocity is the change in displacement divided by a very small change in time, and as that time interval approaches 0, a new idea was born. This idea became differential calculus. Even more remarkably, the Case 2 we discussed later evolved into the finite difference method, which powers modern computer through the field scientific computing. I hope this explanation has clearly shown what differential calculus really means and why the limit as time approaches 0 appears in its definition, using a simple and illustrative idea. We'll explore the derivative of the function f of x equals x squared using a geometric approach. First, we define our function. The function f of x is equal to x squared. Next, we draw a square of side length x to represent x squared visually. Here is the square, with each side labeled x, and the area of the square is x squared. Now, let's recall the definition of a derivative. The derivative of f of x with respect to x is the limit as delta x approaches 0 of the difference f of x plus delta x minus f of x, all divided by delta x. To understand this geometrically, we extend our square by delta x on the right and on the top. This creates two green rectangles, each of area x times delta x, and a small red square in the corner with area delta x squared. We can now see how the algebra works. Step 1, we take the difference quotient, x plus delta x squared minus x squared over delta x. Step 2, we expand the numerator, giving x squared plus 2x delta x plus delta x squared minus x squared all over delta x. Notice that the x squared terms cancel each other. After cancellation, we simplify the fraction to 2x plus delta x. Finally, taking the limit as delta x approaches 0, we get 2x. Thus, the derivative of x squared with respect to x is 2x, which matches our geometric intuition. In this video, we have learned the correct definitions of velocity and acceleration. Many students write velocity as distance divided by time and acceleration as velocity divided by time, but these are not correct definitions. Distance divided by time gives only an average value, not the motion at a single instant. Physics is concerned with instantaneous motion. Instantaneous motion requires derivatives, not simple ratios. Please consider subscribing so you don't miss future videos. And if you think this video could help school or college students, please consider sharing it with them.